All right, so yesterday we were looking to, or starting to solve just very basic first-degree trig equations. We made the connection to a first-degree trig equation to a first-degree algebraic equation, and the concepts are exactly the same. But instead of using inverse operations to get my variable x by itself, we're using inverse operations to get what by itself? The trig function by itself. Right? So we undo any additions with subtractions, subtractions with additions, multiplications with division, divisions with multiplication. We use inverse operations to get some trig function of a variable equal to something else. So you want to see cosine theta equals some number or sine theta, whatever. But then we've got to make one extension to that then. We're not trying to solve for the trig function. We're still trying to solve for the angle. So then how do you undo that trig function? You then use the inverse trig function to find your what? Reference angle. And then you need to apply that reference angle into the two possible quadrants where that function is positive or negative. And then always, with solving equations, the last thing we're then doing is checking to make sure they work. Now, can you check rounded answers with the equal test? No. You just have to type in the left-hand side, then you type in the right-hand side. They're not going to be exactly the same, but are they going to be really close? Yes. Okay. You never, ever, ever solve an equation without checking it. Okay. The last four that I gave you were the multiple choice ones. I want to look at those ones first, and then we'll go up into the other ones. So 31. What did you get for your answer for 31? Choice 3 is correct for 31. 32? Choice 4 is correct for 32. 33? Choice 3 for 33. And 34? Choice 4. So your multiple choice were 3, 4, 3, 4. 3, 4, 3, 4. Okay. Up into number 3 then. They wanted these in degree. What is the angles, or what are the two angles that work in number 3? 270 and 90. 90 and 270. 90 and 270 are the answers for number 3. How about number 6? 45 and 225 are correct. 45 and 225. 90 and 70 for 3. 45 and 225 for 6. How about number 9? Now we're into radian. What did you get for 9? 5 pi over 4 and 7 pi over 4. 5 pi over 4 and 7 pi over 4. If you didn't convert them into radian, you would have 315 and 225. 225 and 315. If you had that, you would have lost a point because you did not have them in the appropriate form. How about number 12? 90 degrees, which is pi over 2 radian. Pi over 2 for 12. 15, they wanted these to the nearest degree. In 15, then, you would have gotten a 24-degree reference angle, which gives you 204 and 336. 204 and 336. 18, you get a 51-degree reference angle, giving you 51 and 231. 51 and 231 for 18. 21 and 24, all they wanted was the reference angle. They just said to find the acute angle to the nearest minute. That's all they wanted was just the reference angle. So 21, it's 82 degrees, 14 minutes. 82, 14. In 24, it's 2 degrees, 52 minutes. 2 degrees, 52 minutes. 27, again to the nearest minute. 84, 34, and 264, 34. 84, 34, 264, 34. And 30, 128, 40, and 308, 40. 128, 40, 308, 40. To the nearest minute. Any repeats that we need? Very good. Questions that we have. 24. My directions in 24 are just to find the measure of the acute angle. All we're looking for is the first quadrant angle that's going to satisfy this equation. Okay. So first and foremost here in 24, do I want my trig functions on both sides of the equation? I do not. So do I want to move the 1 to the 4 or the 4 to the 1? I want to move the 1 over to the 4. So when we do that, how many cotangents will we have? We will have 3 cotangent thetas equal to what? 60. Then we will do what? We will divide by 3 and find out that cotangent theta is equal to what? 20. Okay? And now we're to the point where we want to undo the trig function, right? But do we have an inverse cotangent? We do not have an inverse cotangent. We've got to make a relationship change here. If cotangent is 20, then what is the basic trig function that we know? Tangent theta. Tangent theta is the what of cotangent theta? Reciprocal. So if cotangent is 20, then tangent's got to be 1 over 20. Tangent's got to be 1 over 20. Okay. And now, can I do the inverse trig function? Yes. Theta is going to be equal to the inverse tangent of 1/20th. Inverse tangent of 1/20th. Okay. And again, as you go through that, what one was that again? 2 degrees and 52 minutes. 2 degrees and 52 minutes when you run that through. Okay, that one, Maria? Was it this shift right here? Yep, okay. And again, if you don't have one of the 3 basics, as soon as you get to here, use that reciprocal relationship. Okay. All right, with 24. Nikki? 12. 12 they want in radian. We're still going to find this all in degree. Then we're just going to shift our degrees to radians. Okay. What do the parentheses mean that I have to do over here on the left? I've got to distribute. What are you going to get? 2 sine theta plus 2 equals sine theta plus 3. Okay, do we want our trig functions on both sides of the equation? We do not. 2 to the 1 or the 1 to the 2? And what would we get? Yep, 2 minus 1 is going to be a sine theta. What are we going to do with the 2? We're going to subtract it off. Sine theta is going to equal 1. Sine theta is going to equal 1. Okay. We don't need our calculator for this. Okay. Off of that table that I had you memorize and quiz on every day, what is the angle that has a sine of 1? 90 degrees. Theta equals 90 degrees. And folks, that's not a quadrant angle, that's a quadrant angle. That is the only place where sine is equal to 90 degrees, or sine is equal to 1, is just at 90 degrees. Okay. But I'm losing points here. They wanted it in what form? What do I have to multiply by to change this? So I've got to multiply by pi over 180. Okay, so what units cancel out for me? The degrees cancel out, and 90 goes into 180 how many times? So theta equals pi over 2 radian. Pi over 2 radian. Equal check? Yes, because we didn't what? We didn't have to round, so we can do the equal test on this and it'll work through. All right, with 12? Go to 12. Is there another one we'd like to look at? 27? 27 to the nearest minute. All values of theta to the nearest minutes. And again, what do we have to do with the parentheses in 27? And what will you get when you distribute? 3 tangent theta minus 21 equals tangent theta. Okay, so what are you going to do? And what will you get? So 2 tangent theta will equal 21, and then you'll do what? Divide by 2, so 21 over 2. It is 10.5, but we're not going to change it. We're just going to leave it 21 over 2. How are we now going to undo the tangent? The inverse tangent. So we're going to find our reference angle. And our reference angle is inverse tangent 21/2. But where is tangent positive? 1 and 3. We're looking for a first and a third quadrant angle. Okay, we're looking for a first and a third quadrant angle. So let's go ahead and figure out what our reference angle is. What mode do we want to be in for this, folks? Degrees. Yeah, we want to be in degree mode. And we're going to go inverse tangent, 21 divided by 2. I just did regular tangent, didn't I? Inverse tangent, 21 divided by 2. So there's our reference angle. Now our reference angle is also our first quadrant angle, right? Okay, so let's DMS this. And to the nearest minute, we get 84 degrees, 34. 84, 34. So theta is equal to 84 degrees, 34 minutes, because that's our first quadrant angle. How do we put this into quadrant 3, though? 180 plus that. Okay, so 180 or plus 180, and again, it's going to put me back into decimal, and I need it back into what? Degrees, minutes, and seconds. So option number 4 again, 264, 34. 264, 34. Is our two angles where tangent will equal 21 halves. Now, can I do the equal test when I check? We rounded, so we're going to have to type in this side, see what we get, then we're going to type in this side, and they should be what? Very close to each other. They should be very close to each other. All right, 27? Okay. Today's date is the 11th. Name and date up on the top of those, please, and send those up and over. As you're sending those up and over, I will send this evening's back out to you. So we looked at first degree equations yesterday. What do you think we're going to look at today? Second degree equations. What do we call second degree equations, though? Quadratics. We call them quadratic equations. How many ways do we have to solve quadratic equations? 3 ways. Yep, 3 algebraic ways. What's the quickest and easiest but doesn't necessarily always work? Factoring. We've got the factoring method. What is the process that we can use? The process of completing the square. We're going to stick away from completing the square for trig ones. Completing the square is nice and convenient for algebraic ones, but for trig ones, it gets kind of nasty. So we're going to leave completing the square out. But then we have the generalization of completing the square. What's the generalization of the process of completing the square? The quadratic formula. We're going to stick with the quadratic formula and factoring to be able to solve second degree trig equations. And that's the notes that you want. Second degree trig equations. Second degree trig equations. Okay. Well, yesterday when we looked at first degree trig equations, we first looked at an algebraic first degree equation. Then we made the transition to the trig equation. So let's do the same thing. We know that an algebraic second degree equation looks like what? What's the form of a second degree quadratic equation? Equals 0. And we call that what form? Standard form. ax squared plus bx plus c equals 0 is a standard form second degree quadratic equation. Okay? Well, now instead of having x, we're going to have what though? A trig function. We're going to have a trig function. So a trig function squared plus b same trig function but not squared plus a constant equals 0. Okay? So we're going to have something like this. A sine squared x plus b sine x plus c. We still need to be able to recognize that though as a quadratic. Why? Squared. We still have the square. Okay, so that's a quadratic. Okay, we're going to look to see if we can factor it. But when we factor it, it's not going to be an x and an x. It's going to be the trig function times the trig function. Plus plus or minus plus then the numbers. When we do the quadratic formula, it's not going to be x equals. It's going to be trig function equals. Okay, so it won't just be x equals. Okay, let's take an example of doing this then. I guess we'll review the process here. So factoring if possible. And again, folks, this is what you do always when you see a quadratic equation. You always do what with it? always set it equal to 0. We call that the standard form. We always set it equal to 0, no matter if we're going to solve it with the quadratic formula, by completing the square, or by factoring. We always set it equal to 0. We always look to factor what first? GCF. We always look for a GCF first. If there's no GCF, we look for dots, difference of two squares. All else fails, we go to general trinomial. Now, you would never have one of these as a quadratic, but what if you have 4 terms that don't have a GCF? What kind of factoring is that? Factor by grouping. You'd never have a quadratic with 4 terms, though. You couldn't. Okay? 2 terms would combine together. We're then going to set each factor equal to 0. We solve and we check. Okay. Quadratic formula. What was our quadratic formula? Negative b. Plus minus always comes before a what? A radical. What goes under the radical? B squared. What do we call b squared minus 4ac? The discriminant. And what does the discriminant tell us about the roots? If they're real or imaginary, rational or irrational, equal or unequal. All divided by 2a. Now again, folks, now we're not going to have an x equals, we're going to have a trig function of x equals. And then, of course, we've got the process of completing the square, which for solving trig equations, we're not even going to look at. Okay, it gets just ugly and messy if we're going to complete the square with a trig function. But I do want you to recall the process for it. Completing the square has a prerequisite to it. What's the first thing we do with completing the square? You move the constant over. All we want is the x squared term and the x term equal to the constant. Okay? That's the first prerequisite. The second thing is not something that we always have to do, but we've got to make sure of. X squared's got to have a coefficient of 1. Okay? And if those prerequisites are met, how do we complete the square? Half of the what? Half of the b value, square. Whatever 1/2 of b squared is, it gets added to both sides. And then I've got a perfect square trinomial that I can factor down. X plus or minus whatever half the b value was, squared equals, and then I can undo the square and then undo the addition or subtraction. So that's very good that you remember that process. I'm very happy. All right, let's go. Do you recognize that this is a quadratic? Why? Because of the squared. All right, well, I want this in standard form then. What would that be? Tan squared theta minus 3 tan theta minus 4 equals, is this a more basic one or a more advanced one? Should I try to factor this one or no? Yeah, I should try to factor this one, right? Okay. What multiplies to give me tangent squared? Tangent and tangent. My signs would be different. I need a set of factors that will give me 4. Well, there's only 2 possibilities. What and what? 1 and 4, 2 and 2. They need to do what to give me what? Subtract to give me 3. Will 2 and 2 subtract to give me 3? No. Will 4 and 1 subtract to give me 3? Yes. So we can factor this. We're going to have a tangent theta plus, and we're going to have a tangent theta minus. All right. What's going to give me negative 3? 4 minus 1 or 1 minus 4? 1 minus 4 is going to give me the negative 3, right? All right, so what do you do to each factor now then? Yes, yeah, we always should. I'm glad you brought that up. When we factor, we always ask what? Can I factor further? Can either of these be factored further, though? No. What do we now set them equal to, though? Now, you don't necessarily have to show tangent theta minus 1 equals 0. Can you go right directly to tangent theta equals negative 1? Can you do that? Absolutely you can. Over here, tangent theta is going to equal 4. Tangent theta is going to equal 4. Can tangent equal 4? Yes. What other 2 cannot? Sine and cosine have to be in between there. Why? Because sine and cosine deal with the hypotenuse. The hypotenuse is which side of a triangle? Largest. So if if sine or cosine are greater than 1, that means that your hypotenuse isn't the largest side. That can't happen. But tangent can be because it's opposite over adjacent. Can the opposite be longer than the adjacent? Yes. Can the adjacent be longer than the opposite? Yes. So tangent can be outside. Sine and cosine can't. Okay? So, now we're at the point we were last night, right? We have a first-degree trig equation. I actually have 2 first-degree trig equations. What did we do last night when we got to this point right here? What's that? Yeah, we want to find out what quadrant they're in. We want to find a reference angle. We just have this first degree again. So where is tangent negative? 2 and 4. Tangent's negative in 2 and 4. How do I find the reference angle? Inverse tangent. Inverse tangent of what? Not negative 1? No. The negative was just used to tell us what? What quadrants we were in. Reference angles are always where? First quadrant, where everything is positive. You don't need your calculator. What is the angle that has a tangent of 1? 45 degrees. Okay? So, theta equals then, how do I put 45 degrees into quadrant 2? Subtract off from the 180. 180 minus 45 gives us 135. How do I put 45 into quadrant 4? 360 minus, right? So what's 360 minus 45? 315 degrees. Last night we would have been done, right? But quadratics have 2 sets. I now have to do this exact same thing over here. Where is tangent positive? First and third. How are we going to find the reference angle again? Inverse tangent of 4. This one you don't know. 75 point, keep going. Okay, so theta equals, my reference angle is the what quadrant angle? The first quadrant angle. So we would have to the nearest degree what? 76 degrees. How am I going to put this into quadrant 3? Plus 180. So 180 plus that to the nearest degree? 256 degrees. So folks, we're used to a first degree equation having how many solutions? Just 1, right? But a first degree trig equation can have 2. We're used to a quadratic equation having how many solutions? 2. But a second degree trig equation could have up to 4. Okay, could have up to 4. Do we need to check all of them? Absolutely we need to check all of them. Can I do the equal check with 135 and 315? I absolutely can, right? Can I do the equal check on 76 and 256? Can we do the equal test on those ones? No, why not? We round it. We're going to have to test the 2 sides. We'll type in the right-hand side, see what we get, type in the left-hand side, and hopefully they will be very, not equal, but they're going to be very, very close to each other because we round it. Okay? Folks, I can't stress this enough. You need to go back. You need to take the 2 seconds on the Regents exam and go back and test these. Is it worth losing either a 4th or a 6th of this problem for not checking? Absolutely not. Every single point on this exam is valuable. Those of you that play sports, every possession in basketball is extremely important, right? Every at-bat in baseball and softball is extremely important, right? Every down in football is extremely important. Every possession in soccer is extremely important. Every point on this Regency exam is vital to you. You need to take the time to check the equations that you solve. It is vital. That could be the difference of passing or failing on whether you checked an equation or not. People have failed this exam for multiple rounding errors and multiple things that they did not check. To me, I consider those kind of stupid errors. Why? It was completely in that person's control to check those answers, and they didn't. Okay. Tough to bite a bullet on a 64 when you didn't check your answers to see if they worked. Okay. Make sure you check. Okay. Questions on how we factored this? We've been factoring since when, folks? Yeah, middle school and Algebra 1. We've been doing this factoring. We should be extremely comfortable being able to factor something like this. Okay? Folks, could you even do something like this? Could you say, you know, I don't like seeing the trig function there, so I'm going to do this. I'm going to let x equal tangent theta, and then what would my equation look like? X squared minus 3x minus 4 equals 0. And are we really comfortable with that? And folks, if we're not, we shouldn't be in this level of math. If we're not comfortable with solving that right now, we're above our head. Okay? You just got to make sure at the end then, once you get this solved for x equals -1 and x equals 4, you go back and do what? Replace it back out. So tangent theta equals -1. Tangent theta equals 4. Okay. You can absolutely do that if you're more comfortable with it. Okay. Factoring, questions there? Okay. What method did we use to kind of help us with factoring if it was a little more advanced one? We called that the X method, right? Called it the X method, where we automatically just put the X to both sides. We determined our signs, and then if necessary, what did we divide by? Whatever the A value was, we divided by. What value got dropped right to the top? The B value. And what did we do to get this number down here? A times C. And then you found your factor pair that did this, divided it out by the A, so on and so forth. So don't forget the X method to help you with more advanced factoring techniques. Let's take a look at a quadratic formula. 3 cosine squared x minus 4 equals 5 cosine x. Do we recognize that this is a quadratic? Why? Squared. All right, well, what would standard form be then? 3 cosine squared x minus 5 cosine x minus 4 equals 0. Okay, now, could we potentially look at X method to help us with this one? Yes. Now, don't write this down. Okay, you're just going to walk me through the X method, but don't write this down. We're going to solve this with the formula. I just want to see if we can, though. Okay? So we'd set up the X. And what are we going to have left and right? Not X, but this time, yep, with a trig equation, we're going to have the trig function. Cosine X, cosine X. My signs are going to be, bless you, so one's a plus, one's a minus, and they're both going to get divided by what? They're both going to get divided by 3. What comes to the top? My -5. You don't need the negative if you don't want to. And then what goes to the bottom? 12, because 12 is 3 times 4. Okay, so we've got 1 and 12. We've got 2 and 6. We've got 3 and 4. Do any of those subtract to give me a 5? No, I can't do what? I can't factor this one, but I wanted to set that X method up just so we could see a specific example again and kind of refresh ourselves on how we're going to do this. We're going to solve this by how? Completing the square? No, it's going to look ugly with trig. We're going to solve this with what? Okay, so A is what? And this is important too, folks. Don't forget your negatives on B and C here. -5 and -4 for B and C. Okay? But we said the quadratic formula is not going to be x equals with trig. In this case, it's going to be cosine x equals. Cosine x equals, and you told me before, negative b plus minus the square root of b squared minus 4ac all over 2a. All right, what was our a value? And where does it go? After the 4 and after the 2. What's our b value? First 2. And our c value? -4 at the end. Okay. We do the 2 parts in our head. We let the calculator do the other. Negative is a +5 plus or minus the square root. And in the bottom, 2 times 3 is 6. You will go to the calculator and compute the discriminant for me. Now, I don't want the square root of it. I just want the number that goes underneath it. Okay, so calculate the discriminant for me, please. And we're going to have a little review after you calculate the discriminant for me. Verify a 73 for me. Yes. All right. Are my roots real or imaginary? Why are they real? Because it's positive. Are they rational or irrational? They're going to be irrational. Why? Because it's not a perfect square. Are they going to be equal or unequal? They will be unequal. The only time they're equal, when it equals 0. So we have real, irrational, unequal roots here. Real, irrational, and unequal roots. Okay? And can I break down the 73 at all, folks? No. It's prime. We really can't break that down. Okay? So cosine x is going to be equal to 5 plus radical 73 divided by 6, and cosine x is going to be equal to 5 minus radical 73 divided by 6. Okay, so let's go into our calculator. Now, before I can do the inverse cosine, I've got to know what that actual value is. So let's go and compute it. So 5 plus the square root of 73 is that, divided by 6 is that. Can cosine equal 2.257333958? Absolutely it cannot. We're not going to get anything from that. Do we cross it off and scribble it out or erase it though? No. It's a solution to the non-trig equation, but cosine can't equal that. Okay, so let's change that up then. Let's take 5 minus the square root of 73 and divide that by 6. Can cosine equal that? Yes, it can. Cosine can equal that. Cosine will be negative where? 2 and 3. This will happen in quadrant 2 and quadrant 3. And we're going to have a reference angle equal to, how are we going to find the reference angle? We're going to take inverse cosine. But, folks, I'm not going to take the inverse cosine of that negative. I need to take the inverse cosine of what? The positive value, right? So am I going to have to type it all in? What could I do that would make that positive? Just negate it, right? Negating a negative would make it positive, wouldn't it? Are those 2 button pushes easier than typing the whole thing in? Much easier, right? Much easier. What's our reference angle? 53.795. 53.795 ... Okay. So how do I put that into quadrant 2? Plus 180. So to the nearest tenth of a degree, I'm sorry, did I say plus 180? Yeah, minus 180. The plus will put us into quadrant 3. 180 minus 126.2. And how do we put it into quadrant 3? Add 180 to it. So what's 180 plus that, rounded to the nearest tenth? 233.8 degrees. Folks, what if they wanted it to the nearest minute? What would you have done then? Degrees, minute, second it, and turn it into there as well. Would they ask for it in radian? Normally not. Folks, if they ask for it in radian mode, you're going to come out with nice angles, like the 30s, the 45s, the 60s, the 90s. You're not going to get a decimal answer and ask you to change a decimal answer into radian. That's very, very rare. I don't think I've ever seen that on a Regents. If they want them in radian on the Regents, they're usually nice values, like the pi over 4s, pi over 3s, pi over 6, something like that. Okay? They wouldn't take a decimal one and have you change that. I don't want to say they wouldn't. They might. I've never seen it. So what you're asking is what I have written here enough for full credit? Yes, absolutely. Absolutely it is. Okay. Nice to show it, but you're not losing credit if you don't. Okay. All right. Homework done, folks. We are going to cut that down. If you can solve one quadratic trig equation, you can solve a dozen. But they are lengthy. You are going to do all of 15 through 19. Why are you going to do all of 15 through 19? They're multiple choice, and you're going to do them where? In your calculator. But other than that, you're going to do 21, 33, and 45. Okay, so get rid of those ones. You're going to do 15 through 19, 21. Notice your directions. 21, you're going to use the factoring method. 33, you're going to use the quadratic formula. 45 is at your discretion. All right? So just 15 through 19, 21, 33, and 45. What's due Monday, folks? Your test is due Monday on Castle. Make sure you do that. We have review tonight. Please sign up if you plan on attending so I know. And have a great afternoon.